All right, so let's continue here. The section we're on right now is section 2.6 of the review. And in section 2.6, we're dealing with resonance and formal charge. In the previous discussion, we had looked at identifying a couple of molecules that had resonance. We've alluded to it, but we didn't draw very many in that section in 2.5. But here, we do have molecules that we'll look at, and so essentially what we can draw is, let's go ahead and draw a couple of them here. One example that I want to start off with is, let's just look at the molecule of NO3. It has a -1 charge. So if we're going through the process of drawing the Lewis dot structure, remember here that nitrogen is going to have 5 valence electrons. It's in group 15, -10 is 5. And then we're going to add that to the valence count of oxygen, which is 6, but there's 3 copies of it. And then because we do have a negative charge here, let's go ahead and bring this back. We do have a negative charge here. We want to make sure we bring this down here, and that means we're going to add the 1 electron for that and consider it. So here between these two values here, that's 18, that's 23, and then we add the 1 to it, so that gives us here a total count of 24 valence electrons overall. So the structure that we're going to draw here, if we draw it, is we're going to have to draw it here with a nitrogen. So we're going to draw that nitrogen here. Let's go in the center, and that nitrogen will have a oxygen bound to the top. It'll have an oxygen bound to the bottom, and 1 to the right. At least that's the way I'm going to draw it here. Okay. Since we have 24, let's go ahead and write that number over here on the right-hand side. We've got 24. I've already allocated 6 electrons, 2 to the side bonds, 2 to the top, and 2 to the bottom, so that's a total of 6. And so if I subtract that from the count here, that leaves a count of 18. And when you go through this, you got to make sure that the octet rule is observed, especially when you're considering resonance, because you're not going to see the structure here as a single bond all the way at top. And so initially you want to go ahead and add 6 to the top, 6 to the left, 6 to the bottom, and that'll give you your 18. But when you start to look at the center atom, the nitrogen's not going to have a octet if you only apply a single bond at each of these positions. So what you want to do here is make sure that you consider that this one here is going to have a double bond. And so now nitrogen has the octet in the center. And so if we do that, that means that our original count here instead of 6 will be 8. So our total modified version here essentially is going to be a 16 count. So let's just go ahead and take that. And so now we can apply the electrons here. We'll apply 6 to the bottom. That'll give me 10 left. And so if I apply the other 6 here, that'll give me 4 left. And so I can apply 2 here and 2 there. And so it's this particular structure that is the starting position for resonance structures. And the idea is, the main thing behind resonance structures is, can I draw the Lewis structure but in a slightly different way? In other words, can I put a double bond in a different location other than the one location where I put it into? And so the idea is, yes, you can. And so what we'll do here is, let's just go ahead and draw this right here. So we'll draw instead of a double bond to the top, we'll draw a single bond to the nitrogen, but now we'll put the double bond to the left, single bond to the bottom, and then we can go ahead and draw the other one, which would be the single bond to the top, a single bond to the left, but now we're going to do the double bond to the bottom. And I'm just going to repeat the original structure that we drew up here. I'm just going to write it down here just so we can have them all together. And so that would be double bond to the top, and then a single to the bottom. And so here we would have 2 there, 2 here, 2 over here, and then all the other oxygen atoms are going to have its respective 6 that we normally see with a single bonded oxygen atom. Okay. And so the idea here, if you look at all these structures, is that each of these structures, when you go through and count the oxygen or the electrons, you can see that this oxygen to the top has its octet in the single bonded form. It also has its octet when it's double bonded. And then the nitrogen in each of these 3 cases is going to have its octet as well. We usually represent the resonance structures here with a double-headed arrow in both the directions, and we want to make sure we seal that off with a bracket, and we also designate the charge up at the top right corner, and that charge would be the original charge that was identified here in the molecule. Okay. Now each of these structures here is known as a distinct Lewis structure, but if you were ever shown a diagram of this where it's a unified approach, what you can also see is you can see this is going to be almost congruent here. You're going to see that the structure here can be represented in a slightly different way. I'm going to represent these as single bonds here overall, and then we're going to have a dashed line between them. And since all of these are representing those bonds there, then I'm just going to draw them with 2 electrons each, because potentially each of these is going to have its own double bond. So this would be the unified approach. Now, they're not going to ask you to draw these. I won't ask you to draw that on the exam, but I might ask a question or so that kind of asks you about the bond length. So here, this particular bond here, because it is almost indicating that it is partial double bond coverage, this particular bond here is actually going to be a little bit longer than, say, the full double bond. The double bond here is going to be the fullest, is going to be the shortest because it has the strongest bond energy associated with it. But then the second shortest would be this one over here, which is a hybrid. And then the longest of these bonds is going to be the single bond. So that's just a way of combining some of the information we already learned in a previous unit and applying it here. That's a question that sometimes gets asked, and so you should be prepared for that as well. Okay. Other than that, though, this is the section on resonance. Let's go ahead and kind of zoom in now and focus a little bit about the formal charge and how that leads to whether one structure is preferred over another. And so let's go ahead and take this molecule here. Let me just make things a little bit smaller. And so let's see here. Go there and kind of see if I can make everything a little bit smaller. And I'll come right back. So what we'll do here is I already cleared some space. Let's go ahead and look at a couple of examples here. What if I had a couple of these? I'm going to grab some here from the problem set. So what if I had something like a CO3, 2 minus. Now obviously you want to go ahead and draw this, and this one's going to give you a couple of structures that you should be aware of. And so the structure here is going to be a oxygen to the top, double bonded carbon, oxygen to the right or left, oxygen downward, and then you're going to have your respective oxygens here. 1 2 1 2, 6 of them on the oxygen to the left and 6 to the oxygen to the bottom. And overall here, this is going to be a -2 charge. And so the question here now, let's talk about formal charge, is what is the formal charge? Typically the question is, what's the formal charge of the center atom? So in this particular case, it's going to be carbon. And so what you'll do here, if you remember the equation on formal charge, the formal charge, which is abbreviated FC, is going to be equal to the valence electron for that particular, or the valence electron count of the first atom, or the atom that you're looking at. And then from this, you're going to subtract 2 numbers, or a total of 2 numbers. You're going to subtract the number of bonded, or the number of bonds. And then you're also going to subtract the number of unpaired electrons. Okay. And so if we look at these numbers here, let's go ahead and calculate the formal charge for this particular carbon. So we'll take the formal charge of the carbon is going to be equal to the valence electron count for carbon, and that would be 4 valence electrons. And we're going to subtract this from the sum of the number of bonds. And so here we notice we've got 1 bond here, 2 bonds there, 3 bonds, and then the other bond on the other side. So let's take a look at that one. So that'll be this bond over here on this side. So that'll be 4 total. So now that we've got the 4 bonds there, we can write that in. So it'll be 4 bonds being formed. And then we count the lone pairs. On the carbon atom, there are no lone pairs. Or another way of calling them, there are no unpaired electrons. So that number there in the mix is going to be 0. And so we calculate this out. This essentially is equal to 4 minus 4, which essentially is equal to a 0 charge. So the carbon here would have a charge of 0. Okay. Now, what about the oxygen atoms? What's the formal charge of these? So let's kind of look at the bottom here. It's the same as this over here, though the oxygen to the left is the same as the formal charge for the oxygen to the bottom. And so if we do the math there, let's just use a slightly different color. Let's use green. So for this particular atom here, the formal charge of that one is going to be the valence number for oxygen, which is 6, minus the sum of the bonds. Oxygen here only has 1 bond, and so we'll say 1. And then we're going to add to that the number of unpaired electrons. So we've got 2, 4, 6, And so the number here would be 6 overall. So this would be 6 minus 7, which means that the formal charge for this particular oxygen atom is going to be a minus 1. And so when we write it, we would write minus 1 charge there. That would be the same charge over here, minus 1 to the oxygen to the left. And then the formal charge for the remaining oxygen atom at the very top, we're going to put that, so let me just write it over here. So the formal charge of that one is going to be equal to 6 minus 2 bonds. And so you can see those 2 bonds right here, one on one side and one on the other. And then we're going to add to that the number of valence electrons, or excuse me, the number of unpaired electrons. Here we've got 1, 2, 3, and 4. So we'll add that to 4. So this would be 6 minus 6, which essentially give me a charge of 0 on the carbon, excuse me, on the oxygen to the top. So this is the way that you would want to do this. The other item that you need to take into account here is whenever you're given two resonance structures, the resonance structure that actually is the preferred or the dominant version is the one that's going to have the lowest oxidation numbers assigned to all of the atoms. And where necessary, or where there is a similarity, you always want to allocate the negative charge to the one on the more electronegative atom. That's the one that's going to have that formal charge there. Okay, and so that would probably be the most dominant form of the two. So that essentially is the resonance and formal charge section of 2.6. And so with that, we'll kind of bring this review to a close with the last section of 2.7 here, looking at molecular geometry and hybridization.